Okay, so it's a great pleasure to introduce our final speaker. And actually, this slide was supposed to be in the initial slide deck, but actually it's in a much more appropriate place at this stage, because what we have here is the beginning of the program for the 2021 National Organic Symposium, listing some of the plenary lectures. And in this symposium, there's also a recognition for the most prestigious award that the Organic Division has available, and that is the Roger Adams Award. And I'm pleased to announce that the 2021 Roger Adams awardee is actually today's speaker. And he is such a modest person, Ken Houk, that he realized that when he arrived at the meeting, he didn't have a tie on. So he went back to put on his tie, which just shows what a modest person he is. And I'm delighted to be able to introduce him. He's a member of the CCHF, and he's actually one of the most loyal members of the CCHF. We're rather a crazy group that tends to meet virtually twice a week. And Ken is at virtually every single meeting, unless he's traveling, and now he's not traveling, then he is at every meeting. And he's just a fantastic collaborator and such a great team player. At this stage, Ken is not a great role model for starting students because he has 1,300 publications. So it's absolutely fantastic what he's done, and has such a huge impact in applying computational chemistry to so many different organic transformations, and really helped with our understanding of many transformations, and particularly in the field of CH functionalization. So Ken, it's a great pleasure to introduce you, and looking forward to your talk. Let's see if I have your title in front of me. Computational Studies of Radical CH Abstraction versus Addition to Alkenes, and Ambimodal Cycloaddition Dynamics and Mechanisms. Welcome.
Okay, all set. Thank you, Hugh. Thank you for the very generous introduction. Yeah, I was worried I'd be the first time I ever gave a lecture without a tie, so I got my tie for this occasion. Thanks all of you for being here, and thanks to David Proctor and Masa Wasa for such great lectures. Today I will give a two-part lecture, and here are the titles. Both parts involve computational studies designed to reveal the origins of selectivity, one of the principal focuses of the CH Functionalization Center. Part one is about radical reactions, and in particular about competitions between CH abstraction and addition to alkenes. And the second part is one of our favorite topics over the last decade, about ambimodal cycloaddition dynamics and mechanisms. The first part is done by a visiting scholar from Jiangnan University, Wochao Xu. He's an associate professor there in Wuxi, and a postdoc in my group currently, Arka Sengupta. We're interested in what determines whether radicals abstract allylic hydrogens, for example, the T-butoxy reaction shown here, or add to the double bond, as in hydroxyl addition. This is also important in biology. So P450s can either do something like an addition, that is an epoxidation, or can do allylic hydrogen abstraction. And Sesong Sheikh has recently brought more attention to this by showing that electric fields might be able to alter the preference from one to the other. We became interested in this beginning in 1976. And at that time, Bertrand and Surzer published a paper on proposing that there's a relationship between the electronegativity of radicals and whether they abstract or add. For example, relatively electropositive oxyradicals like the oxygen radical anion or T-butoxy give almost exclusively hydrogen abstraction. On the other hand, as the electronegativity increases, and the electronegativity here is measured by the Mulliken criterion, is the average of the IP and EA. As one goes down this table, with hydroperoxy, for example, equal amounts of addition and abstraction are observed. And as the oxygen radical becomes more electronegative, then addition is observed. With non-oxy radicals, it's a little more complicated. Many of the highly electrophilic do add, but there are some like alkyl radicals and haloalkyl that add in spite of the fact that they have relatively low electronegativity. The hydrogen abstraction reactions have typically been treated by the Evans-Pilani relationship shown here. So this relationship is that the activation energy for a given reaction is some standard activation barrier plus a constant alpha times the enthalpy of reaction. So as the enthalpy becomes more negative, the rate of reaction increases. And this has actually been called variously the Bell-Evans-Pilani principle, the Brunstad-Evans-Pilani principle, both BEP, or the Evans-Pilani-Siminoff principle. And actually, the Marcus theory is a more recent version of that, which is a mathematical deduction of the same kind of principle. In Marcus theory, we represent the reactant potential surface by a parabola and the product potential surface by a parabola. And where they cross is the intrinsic activation barrier when the free energy of reaction is 0. But when the free energy is made more negative, then the crossing here occurs at a lower point and the activation barrier goes down. And the Marcus relationship is that the free energy of activation is the intrinsic free energy of activation plus 1/2 the free energy of reaction plus a higher order term, which is generally very small unless delta G gets very large. So this has been applied to a variety of hydrogen atom transfers. So Brian Roberts published an interesting paper in 1994 where he basically took the Evans-Pilani relationship and added a electronegatividity term. This is the difference between the electronegativities of the two radicals squared. And there's also a term here for conjugation. This is a Evans-Pilani relationship from one of his papers. This is the modified one that shows a much better correlation. We've also treated abstractions from saturated positions and also positions next to unsaturation, and find Bernasconi's non-perfect synchronization operates. So for example, here's a case not for a radical, but for dioxarane insertion into CH bonds, where unsaturated groups or abstraction alpha to an unsaturation have a different kind of Evans-Pilani relationship from saturated. And finally, Jim Meyer, now at Yale, has really written quite a number of papers on using the Marcus cross relationship. So this is another way to write a Marcus relationship, which is in terms of the rate constants for degenerate hydrogen atom transfer between radical X or radical Y. And this is an equilibrium constant for the transfer. So this is the free energy part. And he's shown that for a large number of hydrogen abstractions, that one gets a very good correlation with predictions from this Marcus cross relationship. There's also been the Evans-Pilani relationship applied to radical additions. So here's a review by Fisher and Radom, in which they show that here is a Evans-Pilani relationship for a variety of actually only 2 radicals, but adding to a variety of alkenes. There's a reasonable relationship, but it gets much better when these functions for nucleophilic or electrophilic character of the radical are included. So basically what I'm describing here is the fact that in the background is that Evans-Pilani has been applied individually to abstraction or to addition. What about to the competition? So we've studied a number of these reactions with density functional theory. Here's just a validation of our computation. So experimental log of The ratio of abstraction to addition is the y-axis here, versus our computed differences in activation free energies, according to Head-Gordon's omega B97XD functional with a reasonably large basis set. We get similarly good correlations with the wave function DLP NO CCSD parentheses T, a very popular high accuracy wave function method that's relatively efficient from NASA, and also with the older B3 LYP D3 functional. All of those do quite well for this comparison. I'm going to show you a few transition states here. This is for T-butoxy abstracting hydrogen from the alpha, the allylic position of 1-butene. And this is for addition of T-butoxy to the 1 position. And this is a case where abstraction is favored by about 3 kilocalories. With the more electronegative radical, fluoromethoxy, the transition state becomes earlier for either abstraction or for addition. And now there's a shift towards a more equally balanced activation barrier for the 2 processes. And finally, with the more electronegative ground state of oxygen atom, now there's a shift towards addition being favored. And in this series, the electronegativity of the radical increases, the barriers are lowered, the transition states become earlier, and the activation barriers are lowered more for addition than for abstraction. Exothermicity increases in this case because we're forming stronger CO and HO bonds. So I'm going to talk about studies using of all of these radicals with these various alkenes. And most of our discussion will involve 1-butene, but I've also at the end talked about these other cases where the allylic position is more highly substituted. So first of all, just testing the Bertrand-Surzer idea that there is a relationship with electronegativity. You can see that it's not really very general. It's a little better for pure oxy radicals, that is, that more electronegative tend to add, but still not particularly accurate. On the other hand, the difference in free energy of activation versus the difference in free energy of reaction is better. It's not a perfect correlation, obviously, but it gives a qualitatively good picture of the more, when the reaction becomes more exergonic in favor of addition, that addition starts to become favored. There is this outlier, however. Here are individual correlations just for the oxy radicals. For in green, the addition, so this is the delta G of activation versus the delta G of reaction, just the standard Evans-Pilani relationship. So the addition gives a reasonable straight line, the abstraction gives a reasonable straight line. But in general, for a given exergonicity, the addition reaction has a lower barrier than the abstraction. On the other hand, for a given radical, the abstraction barrier is always, I should say the reaction exergonicity is also always more favorable than for the addition reaction. And here is a Evans-Pilani relationship for the selectivity. So this is the difference in free energy of reaction versus the difference in energy of reaction. And this is a rather good linear correlation. Here's representing the same data, but in a different way, and not all of the data points, but a few. T-butoxy, for example, prefers to add. It's much more exergonic than the addition reaction, and it consequently has a lower activation barrier. As one goes from T-butoxy to the oxygen atom, for both cases, the energy of reaction goes down. The change in the abstraction is relatively small. The change in addition is quite large. And eventually this overcomes the intrinsic preference for abstraction. And for hydroxyl and oxygen atom, the addition becomes favored over the abstraction. So electronegativity is having an influence, but it's having an influence on the reaction energy, which in turn influences the activation barrier. So let's conclude this part by looking at changes in the alkene. So this is T-butoxy. As I said before, with the 1-butene that I discussed, abstraction is favored. But with propene, there's an evenly balanced activation barrier for addition or abstraction. As one puts substituents on the position, so goes to a larger alkyl substituent or two groups alpha to the double bond, then the change in addition activation barrier or addition reaction energy is essentially negligible, but it does, of course, influence the energy of reaction for the allylic hydrogen abstraction, and that lowers the barrier so that it becomes favored. So these kinds of reactions do give good Evans-Pilani relationships. The squares are for abstraction, the triangles for addition, and the circles are for the difference between abstraction and addition, the selectivity. So what I've been talking about so far is the selectivity that's caused by the relative energies of two transition states. So here is a plot where the energy is shown on the vertical axis, and the two transition states would be here or here, leading to these two products. Here's a contour plot for the same thing, showing two transition states that independently lead to two different products. And the products may be interconverted by a different transition state. But there's a different kind of transition state that I'd like to talk about now, in which one transition state can give two different products, this or this. So here's the contour plot. Here's a transition state. And as one moves away from the reactants towards the products, the reaction path bifurcates and can give either product one or product two. And this is a segue into the second part of my lecture, which has to do with ambimodal cycloaddition dynamics. And that kind of transition state is what we call an ambimodal transition state. Multiple modes are possible from one transition state. So the work I'm going to talk about here was done by a graduate student in my group, Cooper Jameson, working with Xiaosong Xua, another visiting scholar from China, this time from Nankai University, and Anna Sommer, who's a postdoc visiting from the University Autonomous of Madrid. And the last part of this part of my lecture is by Fang Liu, who's a professor at Nanjing Agricultural University, and Yu Chen, who's at Nanjing University. So the idea of ambimodal, as we call them, or originally called Bispheric cyclic in this case by Pierluigi Caramella, shown here, he discovered this type of transition state for the reaction of the dimerization of cyclopentadiene. So Pierluigi Caramella unfortunately passed last year. We had a number of excellent collaborations in previous years, although this was the discovery of Caramella and his coworkers at the University of Pavia in Italy. So here's a sketch of the transition state for cyclopentadiene dimerization, and here's the computed transition state on the right. The Bispheric cyclic transition state is so called because it represents a single transition state that can give two different pericyclic reactions. In this case, both the dimerization of cyclopentadiene. But either the top diene can add to the bottom dienophile, or the bottom diene can add to the top dienophile to give the same cyclopentadiene dimer. And the transition state is characterized by one short bond, about 2 angstroms, and two longer equal bonds, about 3 angstroms. And depending on which of these bonds forms, then either the top or the bottom cyclopentadiene is acted as the diene. So this is a transition state that Caramella called Bispheric cyclic, and we called ambimodal. And as one goes downhill past the transition state, this pathway bifurcates to give the two possible products. In this case, interconvertible by a co-prearrangement transition state. We've done dynamics on this reaction, and here's a picture of that. You'll see the first bond is forming first, and then one of the longer bonds in the transition state forms. This looks like it was stepwise, but it's really a two-stage reaction with a very short time gap between formation of the two bonds. Only 11 femtoseconds. That's 11 times 10 to the minus 15 seconds. So we call this a dynamically concerted reaction in spite of the time lag between formation of the two bonds. We've studied a number of these kinds of reactions. For example, We've studied computationally reactions studied earlier by my PhD from Pittsburgh, C.Y. Liu. He went on to an independent career in Taiwan and studied this reaction experimentally. So dicyanoheptafulvene and dimethylfulvene react to give, he observed, products resulting from these last two structures shown at the right, the 6+4 and 8+2 adducts. We've studied this reaction computationally and find the transition state shown here that can lead to three possible products. The first isn't observed experimentally because it can undergo co-prearrangements to give either of these thermodynamically more stable products. So here's a blow up of what I just showed you. Here's that transition structure. I wanted to be able to show you that this is a typical ambimodal transition state. It has one short bond, about 2 angstroms. That's the green bond that's common in all three of these products. And 3 longer bonds, 3 angstroms, 2.8, and 3.2 angstroms that lead to these 3 products. This kind of reaction shows a typical kind of potential energy surface. This is that same transition state shown next to this star. And this is the surface going down in energy. This is the point at which the second bond is being formed. And this is the energy of a structure right here on the shoulder. We call the region here that's circled the region of an entropic intermediate. It's not a minimum on a potential energy surface, but when we calculate the free energy, it turns out that this region is a slight minimum because of the very favorable entropy resulting from many different structures related to this that have essentially the same energy. Here's a case of really what we've found is the champion of these ambimodal transition states. This leads to 4 different products. And this is the result of the work by Xiaosong Xue and Anna Sommer, who were looking for such a tetrapericyclic reaction. And they discovered, after studying a number of different reactions computationally, that this one does give a tetraspericyclic transition state, and dynamics leads to 4 products. So here's a picture of that transition state. The short bond is the gray one, 2 angstroms. That's a bond between one of the positions at of the fulvene and a position on the heptafulvene. But there are 4 other bonds shown in blue, orange, green, and purple that are also around 3 angstroms, and any of those can be formed to give these 4 products. So I'm not going to talk in detail about this, but just to note that we found that actually 2 of these products, the 6+4 and the 4+6, are both thermodynamically unstable, but they can undergo sigmatropic shifts to give these more stable products. And we predict, this hasn't been studied experimentally yet, but we predict that these 2 products or products resulting from 1,5 hydrogen shifts from them will be observed experimentally. So in the last part of my talk, I'd like to pay tribute to Rolf Huskin. So Huskin died this year, 3 months short of his 100th birthday. And Huskin is, of course, very well known for the announcement of the concept of 1,3-dipolar cycloadditions in 1961. And this is a quote from an obituary by Dirk Trauner in Nature Chemical Biology. He notes the enormous importance of Huskin in the area of chemical biology because of what Sharpless eventually called click chemistry and its role in bioorthogonal reactions. But he also studied a variety of other chemical reactions, many cycloadditions, and other kinds of pericyclic reactions. We had the opportunity to discover this year the ambimodal 1,3-dipolar cycloadditions involving a reaction I'm going to show you in more detail later. And we dedicated this paper to the memory of Rolf Huskin. It was published by Feng Liu, Yu Chen, and myself in Angewandte Chemie earlier this year. The reaction we studied was done by Al Padua and Frederick Nobbs and published in 1978. It was one of the first 1,3-dipolar 6+4 cycloadditions. So they generated this 1,3-dipole, a nitrile ylide, by the photolysis of this azarine. And this undergoes a rapid reaction with dimethylfulvene to give a mixture of adducts The one shown here is a 6+4 adduct. The 1,3 dipole is added across the 6 and the 2 positions of fulvene. And the one shown here is a more conventional 4+2 adduct across the exocyclic double bond of the dimethylfulvene. This product is actually not isolated, but it undergoes 1,5 sigmatropic hydrogen shifts to thermodynamically stable isomers. So these workers found a 3-to-1 preference for the 6+4 adduct. We've studied this computationally and found that it involves an ambimodal transition state shown here. And in this transition state, there's one short bond from the nucleophilic terminus of the 1,3 dipole, adding to the electrophilic 6 position of the fulvene. That bond is 2.36 angstroms, and the 2 other bonds that can be formed from the other end of the 1,3 dipole are both somewhat longer than 3 angstroms, so 3.2 and 3.17 angstroms. The shorter one, 3.17 form, would lead to the formation of the 6+4 adduct shown here, the more stable product. And the one to the 1 position of fulvene will give this 4+2 adduct. These products are interconvertible by a 1,5 sigmatropic carbon shift. However, this is rather high in energy, so these 2 products are thermodynamically stable. We've shown earlier that these ambimodal transition states tend to partition past the transition state towards the product that has a shorter partial bond length in the transition state. So this is a plot from that paper in Jack's earlier in a few years ago, where we list the percentage of A in the y-axis versus the difference in the 2 bonds for cases that can give only 2 bonds. And we get a reasonable linear correlation. So we expect in this case that the shorter bond will lead to the major product, as is found experimentally, this 6+4 adduct. But we've also studied this with molecular dynamics. And our dynamics, as you may know if you followed any of our work, involves doing quasi-classical dynamics starting from these points which are in the dividing zone, the transition zone of the reaction. And we run the dynamics in the reverse and forward direction. And then we plot this in terms of 3 different bond lengths. C1 and C2 is the bond that's common to both products. And that tends to be formed first in a transition state, but there's partial formation of the other bonds as well. And then past the transition state, we can bifurcate to give the major product here or the minor product here, shown by the blue trajectories. And we predict about a 2-to-1 preference for 6+4. That compares reasonably well with the experimental 3-to-1 preference for the 6+4 adduct. The reason that this ambimodal transition state is favored is readily shown by this frontier orbital interactions. So the primary interaction is between the high-lying filled orbital of this nucleophilic nitrile ylide. It has quite a nucleophilic center and a larger coefficient at this terminus of the 1,3 dipole. And it interacts strongly with the C6 position of the dimethylfulvene. The other terminus of the 1,3 dipole can interact strongly with both of these positions simultaneously. So that bridges the C1 and C2 positions. And then past this transition state, either one of those bonds can form. So that concludes what I wanted to tell you about today. We started with the talking about the radical CH abstraction versus addition to alkenes. And I hope I've shown you that the Evans-Pilani relationship works quite well for individual reactions, but also for the selectivity. And then I talked about ambimodal cycloadditions, and in particular, the 6+4, 4+2 ambimodal 1,3 dipolar cycloaddition transition state. And we were very pleased to have the opportunity to discover this reaction in Rolf Huskin's 100th year. It's been my pleasure to present this lecture in the 20th CCH Virtual Symposium. Thank you for the opportunity, and thanks very much for listening.
Thanks very much, Ken. Lovely talk. So I'm going to ask you a question which I would not have been able to ask you, okay? Well, I wouldn't have been able to at least make the question, okay? So this is from an anonymous attendee, and that is not me, all right? And the question is, how did the Head-Gordon quasi-harmonic approximation of vibrational energy affect the results? I'm wondering in which cases is it necessary, as it is less commonly encountered in DFT studies than Grimm's correction to entropy.
Okay, say the first part of that lecture again, please. That question again. Not lecture.
How did the Head-Gordon's quasi-harmonic approximation of vibrational energy affect the results?
Oh, okay. So we use the quasi-harmonic approximation to correct for the fact that some of the low frequency vibrations probably give overestimates of the entropy of the species. However, the way the quasi-classical dynamics are done, we start from the transition structure, and then we sample a long motion's perpendicular reaction coordinate and pick various points there. So we don't actually use that Head-Gordon quasi-harmonic correction for that case. So in fact, we don't know the answer to that question.
Okay.
But this is a sophisticated question having to do with how we start the dynamic simulations, which I showed you two examples of in this lecture.
Okay, great. And then a few more questions. Well, a comment, Oliver Thiel says, thanks for a great talk, Ken. And then an anonymous attendee says, thank you for the nice talk. Do you see two imaginary frequencies in those ambimodal transition states? Are they similar in value?
The answer to that is no. The transition structure is, as always, something that has one negative force constant and all the others are positive. So that's one imaginary frequency in that language. It's only as one moves down that valley defined by the imaginary frequency going downhill, but everything else away from that going uphill, that eventually one reaches a point that's called a valley ridge inflection, where that small frequency, positive frequency, perpendicular to the reaction coordinate becomes zero and then becomes negative.
Okay, and then we have one more question. This is from Jorn Hansen, who's actually an old student of mine, who's now a professor at the University of Tromsø in Norway, who says, I like the entropic intermediate. Have you studied how computational methods influence the shape of this region?
We haven't really carried out such an investigation. So we have used different density functionals for the dynamic simulation. Although the entropic intermediate region we investigated that by calculating frequencies along the intrinsic reaction coordinate. And we haven't really done that for very many cases, nor have we compared different functionals for that.
Okay, and there's one final question. It's from Colin Lamb, who's asking, have you applied distortion interaction analysis in the transition states related to the additions versus H abstractions?
Hi, Colin. So Colin was a postdoc with me for quite a few years and now is at Merck in the process group. The answer is yes. We have a really, I could have shown you about 50 slides of that, but I didn't today. So we found that the fairly simple Evans-Pilani relationship seemed to account reasonably for what's going on, although we have done a very detailed distortion interaction analysis, and that will appear in an eventual publication.
Okay, excellent. Well, thanks, Ken, for a really interesting final talk to finish off the session. And I'd like to thank all three of our speakers, David, Massa, and Ken, for making this an excellent 20th symposium, a great celebration of these symposia. So once again, thanks very much. And the audience, thank you very much all for attending and staying with us all the way. Yes, and as I said, we will be announcing future meetings soon, and particularly the next one will be a focus on a more undergraduate focused symposium. So that should be a really interesting event. So with a slightly different flavor. So once again, thanks very much. And I hope everyone has a great evening or great morning or whatever time you're at this particular time. Okay, bye now.